Hello, we are Group B1 and we're going to be covering truth tables. A truth table is a simple method of evaluating a Boolean expression, a Boolean proposition, where you have one or more Boolean inputs and a Boolean output. Okay, so now we're going to show a very simple truth table. Here we have P, and we want to evaluate not P. So here we have true, false, and we evaluate that as false, true. In this video, we'll be using a simple convention of true equals 1 and false equals 0. With our computer science and computer engineering background, this is more intuitive to us. Alright, okay, now we are going to show a slightly more complicated truth table. In this case, we're going to have two input variables, P and Q. And we want to evaluate the output, P or Q. So in this truth table, we have a problem that we have to solve, is how many rows do we need? This is a simple answer. It's always 2 to the n, where n is the number of input variables, which is P and Q. So we can fill this out. One simple way to fill it out is to start by counting up in binary. So we have 0, 0, 0, 1, 1, 0, and 1, 1. Another simple way, as you can see, would be to write the 2 zeros on the left hand and then the 2 ones, and then 0, 1, 0, 1. And if you had more variables, it would be several more zeros and several more ones. So now we have to evaluate this expression. This is P or Q, and it's an OR operator, meaning it's only false when both P and Q are false. So in this case, we only have a 0 in this spot, and we have the rest are 1s.
Hi, I'm Daniel Neese, and I'm going to be presenting how to create larger truth tables and fill them out accurately. So we're going to start out with 3 variables and an arbitrary function. So we'll take A, B, and B implies C, implies C or A. Now, I don't know what any of the truth values are for this function, so I'm going to fill out all the inputs as usual. And what this will allow us to do is go through, and I'll show you how to conveniently work as you go. So what we're going to do is, over here, this is the main operator for the entire function. So we're going to save that to last. The output of the function is dependent on the truth value of this one operator. So instead what we'll do is go back to operators further in. We'll fill those out first, and their truth values will allow us to continue and propagate through the rest of the function. So this, and this are all essentially on the same level. Now, we know that A or B is only going to be false when both A and B are false. So that way, we can just fill out the zeros first and then go through filling in ones for the rest. And we write this under the operator to show that it's the operator that has this truth value. Going over to B implies C, that requires that B is true while C is false in order for the whole operator to be false. Otherwise it will be true. So we look over, and there are 2 locations where that happens. So a 0 here and a 0 here. Then we can fill out the rest of that column. We'll go over to C or A. It's the same thing. So a 0 up top and a 0 2 lines down. So we head over here and to the next operator and fill this out. B, we have 2 functions and we're ANDing those, so we just need to check where we have a 0 value in either, which would be here, 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 and here. The rest of the column being 1s. Now, as you move through, you have to keep track of which you're comparing. So we're going to take these two and compare them with the implication. Again, this just means that we need the left column to have a 1, while the right column has a 0 for the whole thing to be false. And if we look through, this doesn't happen anywhere. So this is how you can easily fill out large truth tables without making mistakes.
Hello, my name is Michael, and I'm here to talk about tautology, contradiction, and contingency. Now, this function right here is, well, we're not sure what it is yet, but we're going to do a truth table and see. Tautology would be is if no matter what the input variable's value is, it is always true. Contingency would be if no matter what the input values is, it is either true or false. Contradiction is no matter what the input values is, it is always false. So let's look at this function and see what we have. Now for 0, 0, you have P or Q, so you have that 0. 0, 1 would be 1, 1, 1. Then you have not P and P or Q. So you have 0 and 1, which would be 0, 1 and 1, 1, 0 and 1, 0. And this would be 0 and 1, so that's 0. Then you have Q, so you just copy the values down over here. Q, 1, 0, 1. Now you have this function implies Q. So for the first one, it'll be true. The second one will be true. Third one will also be true. And the fourth one, false, true, is also true. Therefore, since it is true in all of these columns, or you can also say it's 1 in all of these columns, this is a tautology. Now, if there's a contradiction, like a function like not P and P, which is false in all these columns, then it would be a contradiction. Contingency would just be a normal function, which is false sometimes and true other times, depending on the input.
Hi, my name is Otto Sipe, and I'm going to go over a little bit about the history of truth tables, who invented them, and some better uses to prove some of the things we've already learned in class. So truth tables were first postulated by Ludwig Wittgenstein, and he was cited with their invention in it's a book called the Tractatus Logico-Philosophicus, which was a book published in the early part of the 20th century, which basically proved a lot of Boolean algebra and truth tables. So they're very common today, but they were never used until the 20th century. So I'm going to go over how to prove a common function, which is that if P, then Q. So most people understand how this works, but at least I and many other classmates were a little bit puzzled by this, which is equivalent. So I'm going to prove that with a truth table. So to do that, as my classmates have done before, P and Q are my inputs. Alright, so those are my inputs. First I'll prove this. If P then Q. Alright, so this is only false. As Daniel said before, when the proposition is false and the conclusion, the proposition is true and the conclusion is false. So here it is false. True in all other cases. Now, we can prove the same thing with the equivalent statement, not P or Q, by doing Boolean algebra. So not P, which is equal to 1, or Q is a 1. I'll write this here for you. Now, not P, which is a 1 again, or Q is also a 1. Now, if we not P here, we're going to get a 0 here, and a 0 here, which is going to lead to 0. Lastly, not P, which is 0 in this case, or Q, which is a 1, still gives us a 1. So this proves the often not intuitive relation between if P then Q and not P or Q. Thanks.